There's a mathematical theorem called the hairy dog theorem.
Hairy theorem?
Yes. I mean, that's just jocular terminology.
Right.
Because of something which is topologically a sphere. That means, you see, you imagine a dog shape, but you could sort of move it around with a piece of plasticine until it looked like a sphere. It doesn't have in it. Okay, forget about its digestive system. You see, you're thinking about the surface outside. Mm-hmm. And then the problem is you try to comb the dog all the way around, and the theorem says there's got to be somewhere where it doesn't lie flat. And you try it on a sphere, there's got to be where the hair makes a kind of singular point. It's a bit like that. You have no idea where the singularity is, but you know from general topological reasons that there's got to be one somewhere. And that was the sort of argument that reduced. And I guess people had a little bit of trouble because they'd never seen this kind of argument. And a lot of people picked up on it, in particular Stephen Hawking. And it became, for a while, many people working on it. I guess it's not so popular now because they're probably run out of theorems.
The idea of a singularity, is when you see something like a quasar or the center of a galaxy, mm-hmm. And we were talking about a black hole. When you say a singularity, what exactly do you mean by that?
The normal expectation is that you have a place, like in the middle of the Oppenheimer dust cloud, a point there where the density becomes infinite. And so the curve of space-time becomes infinite. So you have a place where the equations weigh and they go to infinity, and you say, well, something's gone wrong, but maybe electrical cases. But what you could show by these indirect arguments, that somewhere something's got to go wrong. You can't continue the equations of Einstein, and they got stuck.
Right.
So there's a place where they go infinite, or what in detail the theorems don't tell you. They just say that something goes wrong, and that's what we call a singularity.
And if a black hole is larger or smaller, the singularity remains constant?
It remains in there.
It remains in there, but it's not measurable in terms...
Whether you can measure its size very well, because its size, that's an intriguing question. You might say the size has gone to zero,
right.
But it could be quite complicated and irregular, not like the original Oppenheimer-Snyder one, which is even then a point is the wrong point of view, but let's not go into that. No, there is something about the structure of these things you can say. They're not all the same, no.
The singularities are not all the same, but the black holes are not all the same.
They're all the same, but there's one strange things about black holes is that if you let them settle down, they're not all the same to begin with, but there are not many different things they can settle into. They can have rotation, they can have a certain mass, and the mass translates into the size, the diameter of the hole, and you've also got rotation, so they can rotate. And these are... Schwarzschild found the non-rotating ones, and it was Roy Kerr, an Australian, who first produced the solution for a rotating black hole.
Rotating.
Yes, a rotating. But then you see the remarkable, that's what they settle down to. So there are good theorems which tell you that a general black hole, which is very complicated, fairly rapidly will settle down and become one of these Kerr solutions, the rotating black hole.
I remember when I first saw that documentary, and I saw when they were discussing the shape of these galaxies, and that the center of it had this supermassive black hole that was slowly devouring the galaxy.
Yeah.
I mean, it is an unbelievably beautiful yet simultaneously terrifying idea. Is that there's this infinite power in the center of infinite mass that's absorbing slowly but surely everything around it.
Yes, well, it's not infinite. The mass is quite well defined, and it's not infinite. But it's a good question. I mean, if you wait forever, how much of the mass acts swallowed by the black hole? See, I think the picture is to think not to one galaxy, but a cluster. You see, our galaxy has 4 million solar mass black hole, and we are on a collision course with the Andromeda galaxy. And I don't know how long, but some time in the future. Probably spiral into each other, and there'll be one big one.
It's definable mass, but in infinite density, and that this point, where they were speculating that this could possibly, in the center of these supermassive black holes, if you could go through that, there would be another universe.
Well,
is
you
that
see,
just
that's
total
a nice
speculation?
It's a nice romantic thought.
It's more woo. Is it more woo?
I'm afraid so.
It sounds so good, though.
Yes, I know. Well, it's for science fiction because it makes a nice.
Well, it's that we try to make things more complicated than they are because they're so complicated as it is. It's well, like dark matter, for instance. It boggles the mind that we don't really totally understand what 90+%.
Well, that's a question.
Yeah, what is that stuff?
Well, you want to tell you my theory here?
Yes, please.
Well, you see, it's part of a story which, I don't know, about 15 years I must have. Years are passing by, I can't remember how long ago. So I had this idea. You see, the universe as a whole is expanding. Now, early in this century, don't ask me dates again, I'm observing supernova stars, exploding stars, very, very far away. Found out that the universe is actually accelerating in its expansion. And some people found this very mysterious. On the other hand, it's in all the cosmology books because is that expectation. You see, in 1915, Einstein produced his general theory. In 1917, he introduced what's called the cosmological constant. So you think of it was called lambda. You think of a V shape turned upside down, which is a lambda. And he introduced this term for the wrong reason, because at that time people weren't. There was some indication the universe was expanding, but not very clear. And Einstein, I guess, maybe didn't know or didn't believe it. And the Hubble's observations hadn't yet come to make a convincing case of the expansion. So Einstein thought, well, maybe the universe is static. It's kind of philosophically nice to think that it's sitting there all the time. And he couldn't make it do that. So he had to introduce this term called the cosmological constant. And he did that, and then not very much longer after this, Hubble showed the universe does seem to be expanding. And Einstein regarded this lambda term as his biggest blunder, which is an irony, because it turns out that this term is probably the explanation for the expansion of the universe that we now see. So it's what people call dark energy. I don't like the term very much because it's neither dark nor energy in any clear sense, but still, let's not worry about that.
Right. So it's an odd term.
Yes, I think it's a little confusing because there's dark matter as well, which is quite different. You mustn't get them confused. But the dark energy, as it's called, or the cosmological constant, which, as far as we can tell, is completely consistent with the observations. It's a positive number, very small, but seems to be producing this expansion. And I'm quite happy with that viewpoint because it leads to a picture which I've been trying to plug for a while now, maybe up to 15 years, I can't remember. The idea, it's hard to explain, but let me try. It came about because I was worrying about the remote future. And I was thinking, okay, when these black holes are around, they swallowed up all the stars and they're just sitting around. And what's the next exciting thing happening? Well, the Hawking evaporation. They're going to radiate away. Stephen Hawking showed that black holes had this temperature, extremely cold. I mean, these enormous ones are absurdly cold, much colder than anything made on the Earth. And but when the universe expands and expands and expands, it gets colder than the black holes. And so those black holes get the hottest things around, and so they radiate away very, very slowly, this Hawking radiation. And that carries energy, and so they shrink, and they shrink, and they shrink. And finally, they do with a pop. When I say pop, it's probably a pretty big explosion, but not that big from the cosmological, astrophysical scale. So they disappear. Well, it may have been pretty boring when you're sitting around waiting for the black hole to go pop. But afterwards, that's really boring. So this was the picture I thought of being rather depressed by it, thinking that's the fate, you see. The fate of all the interesting things happening. Ultimate fate is this unbelievably boring final state. Okay, this is an emotional argument, but give me a bit of leeway.
Okay.
So I began to think, well, it's not going to be us who are going to be bored, because we're not going to be around. The main things that will be around will be photons. And it's pretty hard to bore a photon. for two very good reasons. One is it probably doesn't have conscious experiences, now that's sure. But the other is more the science point, that they don't measure time, because a photon has no mass. It travels the speed of light, and the way relativity works is that clocks stop, if you like. So if it had experiences, the moment of its creation would be one moment, and the moment would be infinity. And so they just zip out to infinity without noticing a thing. Now, you see, I'd been doing work on this kind of thing, thinking more about gravitational radiation and how you measure its energy like that. And it was a very useful picture to squash down infinity. A useful thing to think about here, if you've seen these pictures by the Dutch artist M.C. Escher.
Yes.
And there are those which are called circle limits. And there's very famous with angels and devils interlocking, and they get all crowded up to the edge. Now, what you've got to think about is that this is a kind of geometry called hyperbolic geometry. And the angels and devils live in that geometry. And the ones right close to the edge think they're the same size and same shape as the ones in the middle. You've got it.
There.
Great.
Yeah.
And so the idea is that if you look at it from the angels and devils' point of view, that's infinite boundary.
Mm-hmm.
But from our point of view, we can look at it and we have what's called a conformal map. That picture is a conformal map. What that means, that little shapes are quite consistently drawn. They can be big or small. And you don't care about whether they're big or they're small, as long as small shapes are accurate, or angles, if you like, are correctly drawn. So it's what's called a conformal map. And that conformal map describes infinity. Now, you can do the same thing to the universe. Well, I see it, you can imagine it, where this remote future, you can squash it down, just like in the Escher picture, to a finite boundary. And as far as the things with no mass, they don't have a way of measuring how big or small it is. The Maxwell equations don't know the scale. They don't care. It does work just as well for small as for big, and you can stretch it in some place and squash it somewhere else, as long as the stretching and squashing is isotropic, so just as much one way as the other way, which means more or less that you keep what I call the light cones there. Let's not go into details here. But it means that if you have things without mass, and most particularly the photons, then that boundary is just like anywhere else, and the photons go zipping up to it, and so you might think they've got to have somewhere to go. Okay, well, you don't have to think that, but that was the point I had, that the photons need somewhere to enter, in a way. But then, where does it go? Well, then there's the other picture, which is opposite end. There's the Big Bang. Now you can do a similar sort of trick there, which is stretching it out and making it into a boundary. And that can be done too. I played with these ideas for a long time, and the standard cosmology model you can do it with. But the more complicated cosmology models, you might have one which is very complicated Big Bang. The general ones don't look like that at all. So you need a condition which tells you that the Big Bang was the very special kind that it was. It's all tied up with this thing called the second law of dynamics, and it all ties together with physics in a way which perhaps we don't have to talk about. But it seemed to me a really good idea to have the condition on the Big Bang that you could do it in the same way. I should say the idea of doing this was a student of mine, Paul Todd, who was a colleague of mine, and he used this as conformal continuation is a nice way of saying what the condition is on the Big Bang to give you what you want. But that's a huge condition. But it's what starts our universe off in a very special state, which is what we live on. Right? It's the second law of thermodynamics needs that to get going. Anyway, I don't know if you want to worry about that. But anyway, the point was that it looks as though it's a good condition on the Big Bang that also should be conformally like a boundary which, if you had no mass, wouldn't notice it. Okay, you've got particles with mass running around near the Big Bang, but as you get closer and closer and closer, the energy goes up, the temperature goes zooming up. They're zipping around at such a speed that the energy of their motion is much bigger than the E equals mc squared mass. Einstein's the energy in the mass is a certain amount, but when they get so hot, you can forget about the mass. So they, like photons, behave like particles without mass, and so they're just interested in the conformal geometry. So the crazy idea I had Not just only you stretch out the Big Bang and you squash down the infinity, but maybe our Big Bang was a squashed down infinity of a previous eon. So I'm saying our eon began with the Big Bang, ended up with this exponential expansion. There was another before us. There will be another one after us. There was another one before that.
Infinite cycle of Big Bangs.
That's the picture.
And constant expansion to the point where there's no more energy, and then somehow or another a Big Bang comes out of that again.
Yes, well, that's the tricky part that people have trouble with.
It's universally accepted that Big Bang was an event. There's no
pretty well
conflicting theories that are attractive.
I would say nothing terribly popular. There are certain ideas which say you can continue into the Big Bang. Paul Steinhardt and
what do they think that was?
It has things in common with my model, but it's not quite the same. And you see, it wasn't right. Not long after Einstein produced his theory, and this Alexander Friedman, who was a Russian mathematical physicist, and he produced the first cosmology model. And one of these was a one which has sort of bounces. Bang, it expands out and then it contracts again.
Yes.
And then one of his models. The only trouble is if you put irregularity to these models, you get black holes, and these black holes form a incredible mess at the end, and that doesn't join on to a nice smooth Big Bang for the next one. So you have trouble with those models. But still, people take these things seriously. And as I say, Steinhardt and Turok have a model which is like that. So these are things one has to think about. My own view is that they don't take into account the black hole problem, which is that my one gets rid of it because the black holes all evaporate away by Hawking evaporation. And so it forms a model. I used to give talk about this, feeling quite happy nobody would ever prove it wrong, so I can go on talking away at it. But no, I wasn't quite happy with that. Maybe you could see signals coming through. So I had one idea about that. But more recently, and this is only just this year, I have two Polish colleagues. That's Krzysztof Meissner and Paweł Nierowski. And there is a Korean who works in New York called Daniel An. And we, the four of us, have a paper which I think today or tomorrow will be an improved version of this paper be on the archive. And the title of the paper is We Seeing Hawking Points in the CMB Sky. Now, what's a Hawking point? You see, I talked about the black hole. See, in the previous eon to ours, assuming it's more or less like ours, there would be black holes in clusters of galaxies, huge, enormous ones, swinging up pretty well the whole cluster. And what happens to the energy of those black holes? Well, it goes out in Hawking radiation. It takes an age. Ages and ages and ages, maybe 10 to 100 years, Google years, or ages and ages. But all that energy in the picture comes out basically in one point. Think of that Escher, and right at the very edge, you see there are an awful lot of angels and devils squashed together there, so that the entire radiation from that single black hole will be squashed into that little. Now we're on the other side. What do we see? Well, there will be a big release of energy at that point, and that we call the Hawking point, and it spreads out. You see, what we see in the cosmic microwave background, this is radiation coming from all directions, and this radiation doesn't come from the Big Bang exactly. It comes from 300,000 years after the Big Bang. So there's a sort of last scattering surface. Photons which are trying to get out finally can escape, and we see them. Now, spread out from the Hawking point to what you see in the cosmic microwave band, in the last scattering surface, is something of diameter of about 8 times the diameter of the moon. No bigger, no smaller. Now, I wouldn't see the whole thing because our past cone, what we see, because to cut across it, we don't see the whole thing. But we see parts of it. So you've got to imagine something from about 4 times the moon's diameter, which is a small region which is highly energetic, more energetic in the middle, and it tapers off as you go to the edge. And we seem to see these things. The analysis that the poles, they have the techniques, and the actual analyzing the data. This is the Planck satellite data. It was done by Daniel An. And then we look at the data and we seem to see an effect which See, we've got only one universe. That's what they complain about. So how do you know if something's real? Well, you make zillions of fake universes and compare this with them. There's a lot of technique about how you do this. But Daniel first did 1,000 of these fakes, and there were sort of two sizes of these. You look at these to see whether the temperature goes out from the outside to the middle. There were two sizes, both within this size that I said, 4 degrees across the sky. And there was no evidence of them at all in the simulation. So this is a real effect. Okay, then people were skeptical for one reason or another. So Daniel did another, 1,000 altogether. And occasionally there are two which do, 2 or 3 to be precise, where you see this effect in the simulations. But if you work out the probability that this is a real effect, you come up with a confidence level of 99.8% that this is a real effect. So we want to see what people say about this.
You've done an amazing job in this book of trying to boil it down for dummies like me, but it's hard. It is a complicated and insanely nuanced subject.
Yeah.
And it's one of those things where it like this many worlds theory, for one example, the just the possibility that there's like, explain that.
Sure.
Explain for people that don't understand what quantum mechanics even means. Give them just like a little bit of that, and then explain many worlds theory.
Good. This is what I'm here to do. So,
thank you.
An electron, take an electron. Quantum mechanics should apply to the entire universe, but it becomes unmistakable when you look at little tiny things, right? So we always are talking about electrons or atoms and so forth. An electron has a position, and well, sorry, let me not even say that. Even that was wrong. It's just so hard to correctly talk about quantum mechanics, right? If you were Isaac Newton, before there was quantum mechanics, there was classical mechanics. And basically, quantum mechanics and classical mechanics are the only two big frameworks that have ever existed in physics. Classical mechanics was so good that everyone thought that was just right, and it was all a matter of filling the details until quantum mechanics came along and changed things. In classical mechanics, an electron is a point. It has a position, a location in space, and it has a velocity. It's moving somewhere. And from that, you can predict what's going to happen, okay? Quantum mechanics says, no. The electron has a wave function. So there's a wave. Sometimes you hear this debate about are things like electrons and photons particles or waves. The answer is that they are waves. And the wave function has this weird property that when you're not looking at it, it's a wave, it's all spread out, or it's localized somewhere, but it obeys an equation, the Schrodinger equation. So far, so good, just like regular physics. There's a thing, the wave function, it obeys an equation, the Schrodinger equation. You can predict what's going to happen next. But the weird thing about quantum mechanics is that there's a whole separate set of rules for what happens when you look at the thing, when you observe it, when you measure it.
That's where it's squirrely with people describing it, right? Woo on you.
It's an opening to woo-woo, right? When you say, like, what do you mean observe something? Like, does it have to be a conscious being? Can it be a video camera? That's just weird, right?
Is it the act of measuring that changes things?
Well, this is the puzzle, okay? This is called the measurement problem of quantum mechanics. That the rules we teach our students at Caltech or anywhere else when we teach them quantum mechanics in their sophomore year of college, the rules say when a system is observed, when it is measured, its state, its wave function, change dramatically, suddenly, and unpredictably.
Now, I'll ask you this. How do we know this based on if you're measuring it and it changes? How do we know? Because we didn't measure it before. Like, what observations are we making that we understand the state of it before it's measured without measuring it?
Good. There's ways. So let me make things even simpler. Forget about where the electron is located and think about the electron is spinning. Right? Okay. The electron is spinning just like the Earth spins. It's really exactly like that. It's like a little spinning top, except when you measure the spin, you can sort of send the electron through a magnetic field and it will get deflected either up or down, depending on whether it's spin up or spin down. You only ever get one of two answers. It's either going up or going down. It's nowhere in between. This is an empirical measured fact. Okay? So that's a part of quantum mechanics. That's the quantum fact, that there's discrete set of possible answers to this question. Is it spinning clockwise or counterclockwise? Yes or no. It's just those two possibilities, nowhere in between. So if you have a magnetic field that is oriented vertically, send your electron through it, it gets deflected up, you say, oh, it's spin up. So now I've measured its spin. Now I know what its state is. If I send it through another magnetic field or oriented vertically, it will always be deflected up every single time. We know what it is. We're going to measure it. Measuring it in this case doesn't change it. It's in exactly that state. We know it, okay? Now let's send it through a magnetic field that is oriented horizontally. So it's going to be deflected either right or left. We know exactly what state it's in. It's spinning this way. But when you send it through that magnetic field that's oriented horizontally, it gets deflected left or right 50-50, unpredictably. There's no way we can predict it. And then once it is, so okay, now it's been spinning up. You measured its spin left, let's say. Send it through another magnet that is going vertically. And now it's 50-50 again. It could be spin up or spin down. So somehow, even though we knew exactly what state it was in, we couldn't predict what would happen next. That is part of quantum mechanics.
Well, the act of sending it through these things where it makes it vertical or horizontal, what is happening to it when it's going through these things?
So quantum mechanics, what we say is that it's not that we don't know whether the electron is spinning clockwise or clockwise. It can be in a superposition of both. That's just the spin version of the position of the electron can be spread out in a wave, right? It's truly just that we are lacking some knowledge. It's that the knowledge really is there. And again, this is how we teach quantum mechanics in textbooks. And then I'm going to correct it because Many Worlds is much better. But This is the standard textbook version. There's a wave function. The wave function for a spin is it's either up or down or some combination. And then there's a rule that says when you measure the spin, you only get up or down. You don't see the wave function. Just like the cloud that you have for the electron's position, when you look at it, you see it at a location. So another way to make the same argument is take a little piece of, I have a nice little image of this when I give talks, a little piece of uranium. So it's a radioactive little chunk of metal, and you put it in a bubble chamber. So it is emitting radioactive particles, and you detect the particles. You can see a little streak of motion when the particle leaves the uranium, okay? Well, like I said, when you're not looking at it, this electron is supposed to obey an equation, the Schrödinger equation. And you can ask what the prediction is when a radioactive nucleus decays and gives off an electron. What is its wave function going to do? What is the wave function of the electron going to be? And the answer is it goes off in a spherical wave. It goes off in all directions at once.
Evenly.
Yeah. All directions evenly. But you never see that.
Is that based on the shape of the piece of uranium? Does it vary?
No, because the electrons from one individual nucleus of an atom, right? So what the uranium is doing doesn't matter. It's just that one atom matters. And the easiest thing for the electron to do is just to go out in a sphere. It doesn't have to. It can go out in higher energy states. But the point is, it's not going out in a straight line. But when you look at it, you see a straight line, right? That's the fundamental mystery of quantum mechanics, that how we describe the thing when we're not looking at it is different than what we see when we look at it.
When you're in pursuit of an understanding, a deeper understanding of quantum mechanics, when you're thinking about people from the 1900s that are just sort of basically getting the first steps going to understand this stuff, when you're talking about this lack of funding and the lack of encouragement for people to pursue quantum mechanics, you strongly feel like there are answers to these questions.
Yeah, that's right.
That we just need better tools and a better understanding, better equations, more time.
Yeah, Einstein, think this, right? Einstein is one of the secret heroes of the book because he has this reputation as someone who just couldn't quite accept quantum mechanics. The title, Something Deeply Hidden, is a quote from Einstein when he was talking about when he was a kid and he had a compass, right? And he was given his first magnetic compass and he could rotate it this way and that way and it always pointed north. And you and I would go, that's cool. But he was Einstein. He's like, wow, this is amazing. Why? How does it know where north is, right? And he said there must be something deeply hidden that explains why it's doing this mysterious thing. And he felt the same way about quantum mechanics, that we gave these set of rules, which are called the Copenhagen interpretation of quantum mechanics. One set of rules for when you're looking at it, one set of rules for when you're not. And Einstein was like, oh, come on. Clearly, this is not the final answer to the nature of reality, right? He wanted to know God's thoughts. He's like, I want to know everything. We're not done yet. There must be more going on. And so Many Worlds is one of the proposed answers to what could be going on. It's not the only one. There's alternatives, but it's definitely my favorite. It's definitely the easiest one to write down. Let's put it that way.
Okay, hit us with this many worlds theory.
So think about this electron. You say that it could be either spin up or spin down. It's a combination of both. That's its wave function. You measure it, you only ever see spin up or spin down. So Copenhagen says that's because the wave function suddenly changed, snapped into place when you observed it. Don't ask me what it means to observe something. That's not what Copenhagen lets you ask.
Okay.
Many world says what you're missing is two things. Number one, you're a quantum system. You're obeying the rules of quantum mechanics. You're made of atoms and electrons and so forth. You have a wave function too, okay? So you're secretly treating yourself as a classical thing when you make that measurement, but you really should be treating yourself quantum mechanically, right? That's one thing. And the other thing is something that Einstein invented, namely called entanglement. When quantum mechanics says there's a wave function for a system, it doesn't say there's a separate wave function for every particle. Right? It says that there's only one wave function for the whole universe. So the way I like to say it is, imagine two particles come in and bounce off of each other. Either one has a wave function and it's, unpredictable exactly what angle it's going to go off at. So both of the particles that go off, you don't know where they're going. But because momentum is conserved, if they came in at equal velocities, they'll go out at equal velocities and in opposite directions. If you measure one, then you know where the other one is going, right? That's entanglement. The observed state of one system can be related to the observed state of another system. So those are the two ingredients. You're a quantum system, and quantum systems can be entangled with each other. So Hugh Everett, who was a graduate student when he invented this idea in the 50s, said, look, when you measure that electron, what happens physically? Like, forget about you're a person, you're conscious, all of that BS. Like, you're a physical system, you obey the Schrodinger equation. You are a quantum mechanical system, you obey the laws of physics. So you look at the electron, your wave function changes. It used to be you're just a person doing whatever you do, but then after you look at the electron, you become entangled with it. And it splits. So there is one part of the wave function that says the electron was clockwise and you measured it spinning clockwise. And there's another part of the wave function that says the electron was spinning counterclockwise and you saw it spinning counterclockwise. Now, everybody knows this. Like that far, it's not controversial at all. That's clearly the prediction of the equations of quantum mechanics. But everyone else said, well, that means that I'm some weird combination of I saw it spinning one way and I saw it spinning the other way, but I've never felt that way. When I look at real electrons, I see them one way or the other. That can't be right. That can't be the final answer. The wave function must somehow collapse. And Everett said, no, what you're missing is there's now two worlds. Both of those part of the wave function are real, but they're different worlds. They will never interact with each other again. What happens in part of the wave function will not affect what happens in the other part. So now there's a version of you that saw the electron spinning clockwise, and there's another version of you that saw it spinning counterclockwise. And that's just taking seriously the prediction of quantum mechanics. It's not adding any extra stuff, any extra worlds, anything like that.
That is the part where my brain broke.
All right.
The idea that there's a you that observes it going clockwise and a you that observes it going in a different direction, like that is so hard to understand. Do you apply this in your regular life? Like, do you think, like when you go home and you say hi to your wife and you open up the refrigerator, do you think of yourself as this quantum being that's existing in this super state?
So there's a couple of answers to that. One is, sure, if I think about it, like I really do believe it. I have a chapter in the book, which my editor resisted at first, but then he let me get away, which is a dialogue between a young philosopher, her father, who is a physicist, and the father is skeptical about all this philosophical nonsense, and she tries to explain how many worlds works to him. And at the end, his last question is, do you really believe this? Are you really taking this seriously? And look, that's a perfectly good question. It's a very respectable question because it is many worlds. It's not crazy or weird or bizarre, certainly very, very far away from our everyday experience, right? So what it's asking you to do is to say, I have these equations. They are really, really good at fitting what I do observe in the world and making predictions. I can build the Large Hadron Collider, etc. I will take them seriously even for things I can't directly observe. because they're the best equations I have, right? Until a better set of equations come along, I will believe these equations. And the implication is, yeah, there's a whole bunch of worlds, like a huge number, like a real, humongously, unimaginably big number, maybe an infinite number, maybe finite, we don't know, of different copies of you, and they're being created all the time. The good news is that it doesn't really affect how you go through your life. It doesn't really imply that you should behave any differently than you would if you just lived in one world.
But do you think of each choice that you make possibly changing everything about the world that you exist in? How are you looking at it? You know what I'm saying? Because you are a guy who probably understands it as good as anybody that's alive. So as weird as this stuff sounds, to me it sounds like it's almost impossible for me to comprehend. So I'm trying to filter it through your understanding of it. Well, we're getting serious.
I know, it's getting hot in here. Physics is heating us up. Yeah, I'm not exactly sure how to say it the best. It doesn't change who you are. It's certainly not true that you making a decision is what branches the wave function of the universe. I guess that's the right thing to say.
Good, because I'll stop all woo.
Yeah, you can't do that.
Before it happens.
Everyone,
Take the breaks.
The joke about how certain political choices imply that we're living in the wrong branch of the wave function has been made many, many times, right? But
okay.
It's not that your choices create different universes. Different universes get created, and maybe you're different in them by a little bit. In fact, I like to point out there is an app you can download if you have an iPhone called Universe Splitter, which will branch the wave function of the universe for you. And then if you agree ahead of time to do one thing in one branch and another thing in another branch, then there will be multiple copies of you who are living different lives. And then you can deal with that in your therapist however you like.
But what is the application exactly doing?
What it's doing is basically a version of measuring the spin of splitter. It's only for iPhones.
I'm going to grab this right now. Sorry, Android people.
Yeah, sorry. It's not even a web page. It's only an app. There's equivalent web pages. But.
Okay, I'm pulling it up right now.
Yeah, and what you can do, basically it sends a signal to a lab that coincidentally is located in Geneva, Switzerland, but has nothing to do with the Higgs boson or anything like that. They send a single photon down a pipe to what's called a beam splitter. So the wave function of the photon goes 50-50. It gets sent left. It gets sent right. And if you agree, and so then it sends back whether you ended up in the branch of the wave function where it went left or where it went. There you go. 199. Come on.
Yeah.
The power of changing the universe is in your hands.
I got it. I paid for it. I got it right here.
Yeah.
All right.
So if you have any tough choices, you can type in, I want to have pizza or I want to have Chinese food for dinner tonight.
Well, it says in the other one I will play it safe.
You can correct those. You can fill in whatever you want.
Really?
Yeah, that's the good part.
But what is happening with this
I will
app?
ask her to marry me. I will not ask her to marry me.
Is
right?
this
I will accept this job. I will go somewhere else.
Equivalent of a quantum fortune cookie?
Possible fortunes are obtained in different universes. The bad news is you can't ever find out how things went in the other universe. You can't talk to the different universes.
That's the problem, right?
Yeah,
so people will be paralyzed by analysis.
That's why you should act the same as if you just lived in one universe, because you can never talk to the people in the other ones.
Now, let's hit the brakes on the woo again.
Yeah.
Because people would like to believe that are there an infinite number of yous existing at the exact same time, making various choices which send you off in different directions?
So, number one, we don't know if it's infinite number or just really big, but there's certainly a really, really big number. It's big enough to be, big enough for whatever. But it's not everything. The theory does not say everything happens somewhere, right? The theory says the Schrodinger equation is obeyed. There's an equation that is obeyed. So electrons will never convert into protons because electrons are negatively charged and protons are positively charged. And nowhere in the Schrodinger equation can you violate the conservation of charge, right? So there's plenty of things that don't happen, but then there are plenty of things that do happen. And some things are more likely than others for you to experience. So again, it's sort of it's a mind-bendy thing, but it's a straightforward prediction of the equations, and it doesn't affect our lives. There's no rule that says, to be a moral person, to be a good utilitarian and make the world happy, knowing that the wave function is branching into multiple copies, I should act differently somehow. It's exactly the same as it would be in the ordinary world.
And you are the ordinary world, no matter how many copies of you there are, or how many versions of you there are.
Nothing. So when all these copies are being made, There's no essence of you that is traveling through one of the copies, right? Like all of these people are separate people. So I use the analogy, it's like identical twins. They were the same zygote or whatever, and now they're different people, okay? So that's the same thing. Like you're you now, and if you hit the button and branch the function, there'll be two different people, both of whom used to be you, but they're not the same person anymore because different things happen to them.
When people think about the concept of quantum mechanics and the way you're talking about it, describing things in the micro and the macro, you think of your existence itself very similar, in a very similar manner, the way you think of electrons, the way you think of things being quantum, is that you are a combination of all these quantum things.
Yeah.
So you don't operate in some sort of static state that's very like here and now and carbon, and you could put it on a scale and it will never change. There's constant versions of you.
Yeah, it's kind of whooshing where, you know, more versions of you are being created all the time. And it's an interesting thing because even the best trained physicists sort of think intuitively classically. Like, look, here's a table, there's a bottle, right?
You have to.
You have
Red
to.
light comes, hit the brakes.
And this is how we evolved, right?
Yes.
This is how our brains work, right? And like I said, you know, many worlds is one respectable version of quantum mechanics. There are other respectable versions, more respectable than the textbook presentation. But they all the other ones somehow lean on our classical experience. And the textbook version certainly does. It says, like, you're a classical person observing a quantum mechanical system and so forth. And Everett, when he was a graduate student, you know, he had arguments across the ocean with people in Copenhagen, you know, who tried to push their way forward. And he's like, why do you get to be classical and the electron has to be quantum? Like, why aren't you quantum? Like, why isn't everything, what's so special about you, really?
Right.
And he was trying to think of the quantum mechanics of the whole universe, right? Where you're not a separate observer outside because he's doing the whole universe all at once. And so everything had to be quantum. And I think that that's another thing that is pushing us to appreciate the foundations of quantum mechanics a little bit more, is that we're trying to understand quantum gravity. We're trying to understand quantum cosmology, the universe all at once, obeying the rules of quantum mechanics and the conventional Copenhagen theory.
Massive black hole at the center of every galaxy.
Yeah.
But there's also other black holes that aren't necessarily in the center of galaxies.
Yeah, so these little ones, well, you know, they're a few times the mass of the sun, and they're from collapsed stars. So they are stars at the end of their life, very bigger than the sun, more massive than the sun, but they run out of their fuel and they start to collapse because gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point, right? Essentially an infinitely dense point. We don't really know what happens we don't know what happens right in the middle. But they collapse to such an extent that there's a region around it from which light can't escape. And so nothing can escape. And that's a black hole.
And what happens to them? Do they travel? Are they moving through space?
Yeah, they're still stars.
Right.
You know, so they're still there. They're surrounded, this region where if you fall in, it's called the event horizon. And if you go across that horizon, then you are going to the center. There's one way of thinking about it, which is quite cool, which is that the time-space sort of flip is one way to think about it. So in the same way that we are going into the future now, so we're going to tomorrow. Nothing we can do about it. We are going to tomorrow. In the same way you fall in across the event horizon of a black hole, you are into the middle, the singularity it's called. So that's your future. Every line of your future points to this of the black hole. So it's kind of the ultimate of no escape, the ultimate prison. You're going to get squashed to an infinitely dense point.
Not every star becomes a black hole at the end of its life?
Because if something like the sun,
we have a small star.
It's quite small, yeah. And when it collapses, there's a sort of a pressure, a force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. But essentially what happens is that, so as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way, if you like. And that makes a force which holds them up. And so that creates what's called a dwarf star. So you can have a blob of matter. They're about the Earth, but they're about the mass of the sun. And so that's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron, which is the same thing, but for neutrons. And they move faster and faster. So if it's massive enough that it overwhelms the electron thing, then the electrons sort of fork into protons and turn into neutrons, and the whole thing starts again. So a neutron star can be, at least 1.5 times the sun, let's say, but it can be about 10 across. So that's an incredibly dense ball matter held up by this. The neutrons moving around. It's got a name. It's called neutron degeneracy pressure, but that's what it is. But if even bigger, then even that can't hold it up. And as far as we know, then there's no known force that we know of that can hold the thing up if it's too massive. And so that's when it just almost winks out of distance, if you like. It collapses and collapses and collapses. And that's when you get a black hole.
We try to put that in perspective. The sun is 1 million times bigger than the Earth.
Yeah.
And this neutron star is, would you say, 1.5 times the mass of the sun,
so
but 10 miles wide?
Yeah. So and to those around, they're called pulsars. So we see those all over the place. The first one that was discovered was called LGM1 because they spin very fast. And it was called LGM1 because it's a very regular pulse, and they thought it was little green men. So they kind of jokingly, little green men one. And so we've seen that there's one called the Crab pulsar, which is in the Crab, which we saw the supernova explosion. So that's when one of these stars explodes at the end of its life and then collapses to form a neutron star. And we saw that in 1054 AD.
Wasn't there some speculation that our solar system at one point was a binary star system, and that one of those stars had become a dwarf?
I don't know.
Someone had read something about that in relationship to the dense object they believe is outside the Kuiper belt.
Yeah, bits of evidence that there's something out there. Yeah. Because of the periodic extinctions and things on Earth, like you get periodic bombardments from out in the Kuiper belt. So yeah, I think one of the theories is
periodic extinctions.
Well, yeah. So for example, like there have been mass extinctions on Earth when a lot of the life died, and we don't know what caused all those, but sometimes they're impacts from space. That seems clear. And so there are theories that there's something orbiting out there which can disrupt all these objects out in the Kuiper belt that sends loads of comets and asteroids inwards to the inner solar system and can cause look. And so there's some people look at those theories.